Alright, so the next experimental design that I want to briefly go over is a randomized block design. And it looks a little bit different than a completely randomized design because a randomized block design actually is an experimental design that will compare treatments denoted as T in blocks, which is denoted as B. So our treatments are randomly assigned to experimental units within some sort of block. And so it's really important that each treatment appears equally in each individual block. So a block is really important because it will actually be used as an experimental design because there is a known source of variation that we know ahead of time as the researcher. So some advantages to using a randomized block design is that first and foremost it's really useful for comparing treatment means in the presence of a single extraneous source of variation. Okay, so a good example of this is the effect of PIN on total weight gain. So, for example, if we were doing a nutrition study where we were comparing ration 1 with ration 2, and we fed that ration to weaned beef calves for 90 days, and we were interested in how much weight they gained total as our dependent variable. One thing that might be an extraneous source of variation would be the breed of the animal. So if we had a mix of like Hereford and Angus animals in this study, we would need to make sure that there was an equal amount of Herefords eating treatment 1 and treatment 2, and an equal number of Angus animals eating treatment 1 and treatment 2. So our block here becomes breed. And so this so that's just a really quick example of what a block would actually account for in an experimental design. And so another advantage of a randomized block design is that the statistical analysis is fairly straightforward and simple. It's easy to construct, and it can be used to accommodate any number of treatments in any number of blocks. Some disadvantages are that experimental units within the block must be homogeneous, meaning that they must be as close to possible, or as close to the same as possible. And so that means that this RBD design is best suited for a relatively small number of treatments. So probably 3 to 5 treatments is all you would want to use with a randomized block design. So the controls are really the only source of extraneous variation, and that's what we are looking to test here. And the effect of each treatment on the response variable must be approximately the same from block to block. And so that within treatment variability that we calculated as part of the analysis of variance becomes really, really important in a RBD design. So the randomized block design model looks similar to a completely randomized design, but we added in one more source of variation here. And so this is the source of variation associated with the block. So we would then look at the sums of squares between blocks in an ANOVA analysis, which adds an additional line to our ANOVA table. Alright, so our randomized block design is going to have, when we go through the analysis process, we're going to have 4 different sums of squares values. We're going to have the total sums of squares between the treatment, sums of squares between blocks, sums of squares between the error. And so our ANOVA table gets a little bit bigger. And so the ANOVA table is what we are trying to generate while using the analysis of variance. And so in a completely randomized design where we didn't have a block, this block row would go away and we would only have the treatment row and the error row. And so the number that we're really interested in is the probability value down here. And when calculating analysis of variance by hand, we would calculate an F statistic and then use an F table to figure out the probability value. And so with a randomized block design, because we have this extra row of information here associated with the sums of squares of the block, we will actually generate 2 F statistics and 2 p-values. And so if we have a p-value that is less than 0.05 or is significant for the block, that means that the blocks were actually different from one another. And so it's good that we looked at the variability associated with the block. Alright, so that should give us a little bit of background on the 2 basic experimental designs and as well as analysis of variance. The third single factor design, Latin square, is going to be in a separate video lecture. Alright, so if we wanted to look at a quick example of a randomized block design scenario, we could do that by looking at this data set here. So in this data set, we have 20 individual experimental units. So the data is kind of set up in two sets of rows. So we have goat number and weight of the goat. Okay, so here's 1 through 10, and over here is 11 through 20. And so in this study, we've got 4 treatments, and we have 5 blocks. And so the blocks are actually weight categories. And so we call this being stratified by weight. So the way that we would reorganize this information before the analysis process is by looking at goat ID number in the first column, their response variable or weight in the second column. Then we would block these guys out. And so so this data is organized from smallest to largest in terms of weight. And so we've got small goats down here. They would be block 1. We have large goats down at the bottom of the slide. They would be block 4. We could then go in and assign treatments to each individual experimental unit. And so we have 4 treatments, A, B, C, and D, and you'll notice that they are randomly assigned in this last column, but each treatment occurs within each block. And so when we would go through and analyze this data set, we actually get an ANOVA table with values that look like this. So here's the sums of squares for the treatment, the block, and the error term. Our degrees of freedom associated with that data set, our variance associated with that data set, and then our 2 F statistics. And what we see is that for treatments, there was no significance because this value is greater than 0.05, but our block was significant, meaning that there was a source of variation among the weights of the goats. So it is a good thing that we stratified by weight and blocked those goats based on weight. And so this is what an analysis of variance table would look like for a randomized block design. It would have 2 probability values. So keep in mind that it would only have 1 probability value for a completely randomized design. Right, so a randomized block design, its purpose is to block to increase precision. And so the cost of using a block in the statistical design is that we will reduce the degrees of freedom of error by 1. So we only use a randomized block design for thinking, or when we think that the loss of a degree of freedom of error will be outweighed by a reduction in the error variance. So it's a trade-off value. So it is possible to use more than one criteria as a basis for allocating blocks to units. So in the previous example, we used just weight, but we could have used weight and age or weight and birth date to create those blocking systems. And so it's really important that thought be given to the possibility of an interaction between blocks and treatments. All right, so that wraps up the completely randomized design and the randomized block design part of single factor designs. And so Latin square design will be the next lecture. And it looks quite a bit different from a CRD and an RBD, but all of these designs are single factors, so they're testing one level of treatments.